There are no reservations in the front row, and it's always nice to see people in the front row, so we don't bite, or we'll do our best. Are we ready to start? Yeah, cool. Good afternoon, ladies and gentlemen. On behalf of the Czech Institutes of Cybernetics, Informatics, Robotics, no, robotics was first, and prg.ai, I would love to welcome you at this event, the Young AI Research Forum. My name is Lenka Kučerová, and it's my honor to be the moderator today. This forum is a product of 4 women, namely myself, my colleague Eliška from prg.ai, and then Eva and Teresa from CIIRC. And we have never written a line of code or submitted a research paper. What we have in common, though, is unwavering passion for the support of researchers in general, and researchers that are eager and proactive in exploring various opportunities to broaden their horizons in particular. Our goal was to bring together this type of researchers more closer to the beginning of their academic career, so they can learn from one another and share useful and interesting information, knowledge, experience from across areas and topics that are relevant to all, irrespective of their research domains. And so they can forge new relations. The capacity of yours to network, exchange, and discuss remains to be seen. But I think that we've managed to bring that interdisciplinarity and variety to this room. So just to kind of check who is in the room, how many students, not PhDs, but actually master students we have in the room, or bachelors? Is there a student from the grammar school who registered also? Yay! Well, applause to that smart guy. Welcome. How many PhDs do we have? Students or who just finished? Great. How many postdocs do we have in the room? More senior than postdocs? Great. How many people are not Czech or Slovak? Great. And I know that we have a dominance of the Czech Technical University in the room, but still, how many people are from the Faculty of Electronics? Quite a few. Information Technologies? Nuclear Sciences? Great. Any other? I've covered it all. How many people do we have from Charles University? Great. The Academy of Sciences? Fantastic. And how many people do we have from international universities? Great. Well, welcome. The clicker's not working. Can you? Oh, here we go. Yeah. So we had the idea for this event in our heads for quite some time, but what finally gave us the catalyst was actually an event called DNY AI, or Days of AI, which is running across the Czech Republic as we speak. It started on Monday, and there are over 200 events in 24 cities in the Czech Republic. With numerous target groups, be it students, academics, people from the business side of things, public sector, general public, seniors, kids, teachers, we have them all. And of course, our goal is to, again, broaden their horizons and introduce those who actually don't know that much about AI into this very interesting world. A few logos needs to be done. It's organized by the recently founded Czech National AI Platform in cooperation with Czech Invest, which is a government agency. And as you can see, we are represented in each of the 13 regions in the Czech Republic. We have some great sponsors, and I would like to thank to all. And what makes us really happy that our hard work and effort has been recognized by validation of important institutions, including President of the Czech Republic. Days of AI are happening because of the logos you've seen. This particular event is happening because of generosity of 3 separate projects funded by the EU. RICAIP, which stands for, Research and Innovation Center for Advanced Production. Then we have CTU EDIH, European Digital Innovation Hub. And then, last but not least, Indo-Pacific European Hub for Digital Partnerships. And now I would like to give word to the director of RICAIP, Mr. Tilman Bergbe, who arrived from Germany, not only because of this, but especially for this.
Thank you. Well, it's a great pleasure to welcome you all here. On the premises of RICAIP, you might have noticed all the machines in the background, and allow me to say a very few words about where you are and what we are doing here. And I think this should be working. So first of all, it's a network. So it's not just the site you see here. We are collaborating primarily with our colleagues in Brno at SciTech, at BTU, who have a similar installation here that we call a testbed. It's really a big laboratory. And then our partners in the EU project in Saarbrücken, DFKI, the German Research Center for Artificial Intelligence, where I originate from, and a second institute called ZIMA. And we have extended that network to collaborations with Ostrava, to the Fraunhofer Institute in Dresden, and to our colleagues in Kaiserslautern, who are also running a smart factory, another big lab about advanced industrial production. So in terms of finances, why is that so big? Because we have a lot of money that the EU invests to start centers of excellence in the so-called widening countries, which include the Czech Republic, barely, because it's very advanced, but not as much as the average. So it's eligible for this kind of funding. And a lot of that money went into infrastructure. Similar projects in other areas built their own buildings. We're part of CTU, of the CIIRC Institute. So all we had to do was renovate these rooms here and in the basement and fill them with interesting infrastructure to play with. That's called a lab, where you do experiments. And what we do goes beyond just the academic research. So it's building tailor-made solutions, putting different robots to work together and figuring out on all the levels how to do this in a systematic way. But we provide not just research, but also put this into innovation and implementation at industrial customers. So we're trying to bridge the whole way from basic research to actual applications in industry. But of course, at some point, industry needs to take over. So we're not running our own startup here. There are startups coming out of this. So this is something you should all keep in mind during your career. If you find something that should be made to work, do it. But then the one advice is think big. Don't think Czech Republic is my market. Think the European Union and then the world is my market. But we do this in a big team. So it's not just people working with one robot and one researcher, but it's teams smaller and bigger working together to integrate systems. That's really the challenge. If you want a whole factory to work, no one single person knows what it does, knows all of what it does. So it needs people to work together. And this is what we do here. And a big problem in the widening countries is that there is existing equipment that you can't just throw away and buy a new robot, because that's too expensive. So building up existing hardware and adding just the digital part to it, to integrate it, this is one of the big challenges. The testbed itself is run as an open access facility. So if you want to do research here, talk to us. We're happy to collaborate with everyone and anyone. If you are a big customer, we're even more happy. But even if you are an industrial customer, this is open to you in principle. Our own research has priority, of course, but there are open access rules. And we work in a number of projects like EDIH, but also in TEF, the Testing and Experimentation Facility for Manufacturing in Europe, with other European customers, so that industrial companies can do test before invest, play with something here, see what will work in the factory, and only then go and buy the expensive robot. And I'll stop here because if you are interested, talk to me or Eva or Teresa. We're certainly find a opportunity for you to visit all of this, but you have a full, exciting program for the evening. And I'll stop here and leave you to that program. Thank you.
I'm pressing something wrong. Obviously, I'm not the technical person. What do I? You are pressing the arrow, right? To the right. Ah, here we go. So just quickly about the program, we wanted to make it varied and ensure that you will have the opportunity to learn, hopefully something new, and also show off because you are still researchers. So we wanted to give you the opportunity to either show your research in poster sessions, which is just at the back of the room, but also share during short pitches. We have two great keynote speakers, and last but not least, you'll have the opportunity to exchange ideas and further kind of explore various worlds during discussion tables, which we call world cafes. Without further ado, I would love to invite on the floor the first keynote speaker, Pavla Hubalková. Just very quickly about the topics we've selected for this evening or afternoon evening. We actually made a kind of survey and got feedback. And building a strong research brand was actually a topic that received most votes. And when we are looking for a keynote speaker, we are actually not looking because she was the only one we could think of. The sky of science communication in the Czech Republic used to be rather dark. And about 4 or 5 years ago, this blazing sun appeared and has been shining ever since. I will let Pavla introduce herself in greater detail. One thing she may not mention is that for her efforts, numerous efforts, she recently received the award of the Research Popularization Award granted by the Council for Research Development and Innovation of the Czech Republic. The floor is yours. Thank you very much.
It's my great pleasure to be here and talk about science and science communication. And maybe we have an adjustment of my mic. Is it better? Thank you. So I will talk about science and science communication. And I will start with a brief introduction, and I will use these two images. Do you have any ideas about what these might be? Do you have any ideas? On the right and on the left? It's an electrophysiological recording of neuron, and it's also my way how I got from science to science journalism, because I wanted to be a scientist. I studied clinical biochemistry and chemistry teaching, and I finished my PhD in neuroscience. I did lab research at various institutions in the Czech Republic and abroad, and the most important experience was my Fulbright internship at Northwestern University in Chicago, where I discovered professional science communication, and I realized that that's it. I wanted to be a science communicator. And that brings me to the image on the right. It's an voice recording of an interview. And I became a science journalist at Charles University in March 2020. It's an easy day to remember because it was the first day of the COVID pandemic in the Czech Republic. So it's kind of accelerated my career. Right now, I'm a freelancer and I'm a science editor at Wired. Do you know the Czech edition of Wired? Okay, so I have a special promo code for you that you can subscribe for use promo code Young AI Digital or Young AI Print, and you can use and enjoy our text. And I would love to invite you as a collaborator, because we give a space for scientists who wants to share their research. So if you want to share your ideas or your comments, something important, let us know. And I also co-authored a book. It's a practical handbook on science communication. We skipped all the technical or all the historical background and theories, and we focus on practical skills and tips how to communicate your research. And today, the topic is clear. It's how to build a strong research brand, and I will focus on science communication because, in my opinion, it's a key. So let's start with the phrase science communication. What's the first idea that comes to your mind? Do you have a mental image?
Distortion of science.
Okay, interesting. Any other? Okay. And how about this? Because for so many people, especially in the Czech Republic, it's something like that it must be funny and that it's something extra and not important. But in my opinion, science communication has many formats and styles, and it's really crucial for your career. And I will give you some tips how to do it in a good way and in an effective way. Because I know that being a scientist in the Czech Republic is tough, because the Czech academic environment expects that you are a superhero, that you are good at science, good at teaching, good at grant writing, HR, grant administration, and science communication. And at the same time, you have a family and a lot of hobbies. In this talk, in this short lecture, I will give you tips how to do it effectively, and I hope that I will give you an examples that science communication is a really crucial part. Okay, for successful science communication, there are a few questions to that you should answer to create a communication strategy. And that's who, what, why, when, and how. And because of time limit, I will start with the most important question, and that's why. It's every child's favorite question, and it should be also the most important question for you. Because to know your why you want to or have to communicate your science is really important, and it's a driving force and source of energy for your work. So why? Science is not finished until it's communicated. It's the quote by Sir Mark Wolpert, and I really liked it. Because you have to communicate your research in a clear way to get funding. And it's much better to practice at students or practice with the general public and not with the grant committee. And I like the examples from Nobel Prize laureates who share that science communication to the general public is the best way how to it's the best way, because the general public asks them weird questions, the question that they would never ever receive at a scientific conference. And these wild questions made them think and inspired them to maybe start a new project. The next why is that science communication help you with networking. And these days, science is really multidisciplinary. So you as an AI expert, you have to talk with biologists or maybe medical doctor. So that's it. The third one is that you might be an expert on a topic that is currently making headline. And it's your duty to communicate, provide explanation, and share your expertise. Otherwise, there would be non-expert, and then you would be pretty sad that he or she talk stupid things about your topic. So please be brave and communicate with journalists. The next one, with science communication, you will be a better teacher, and not just a teacher at school, but also you will share your results with your colleagues at scientific conferences. And I guess that everybody knows stupid or like boring lectures or I remember boring lecture when I was lost on second slide. So please, it's really helpful to share your results. The next one is that you might choose science communication to entertain and share the passion and show that science is cool, exciting, and share it with the general public. And especially in the Czech Republic, you have many opportunities to promote science at various events. And last but not least, you might want to inspire the next generation of scientists. And again, it's super important. But there is one more why, and I will use the example of the COVID pandemic, because there were a lot of medical doctors and scientists who talk about all the molecular biology and about mRNA and spike proteins and so on. And for them, it was really fascinating. But there were people like my grandma, and she was more concerned about possible side effects. She wasn't interested in spike proteins. So please answer and explain all the stupid and obvious questions for you, because the general public needs to know and hear from you as an expert. Otherwise, you create a space for misinformation and alternative facts and alternative theories like microchips and so on. So please be patient, repeat and explain again and again and answer the why question that might be obvious for you but super important for the general public. And the second most important question is how to communicate your research. But we have to go back and we have to start with who. Because who is your target audience influence everything. It influences your style and format. Take this example. Take the example of a house. Let's imagine that you study this tiny window. And when you talk with your colleagues, it's okay to start talking about this tiny window because your colleagues know. But at a scientific conference, you might have to talk about all the windows and explain that there are a lot of windows and yet you study this one. But with the general public, you might have to start with the foundation and then build the knowledge floor by floor. And then at the end, you will talk about your window, because you have to explain the context, because it's not just about the window, it's about all the, because it depends on the building and the context. So it might happen that for various audiences, you have to talk about different things. And you will spend most of your time talking about the basic principles and explanation of the whole field. Okay, so how to communicate your research? First of all, I will give you a list of options, and then I will give you I will talk about the translation, how to translate scientific project to the language or stories that the general public can understand. So first option, it's web pages. For some people, it's like an ancient technology, but in my opinion, it's really underestimated. And it's a great source of it's like an archive for you, for your work. So improve your web pages, update all the information. And if you have no power to update like your institutional web pages, create and update LinkedIn profile. Do you have a LinkedIn profile and do you have active and updated LinkedIn profile? So please do it in the evening. Just update your LinkedIn profile. It's really crucial. And it's really helpful for networking, and my colleague will talk about it later. Social media. Who is active on social media? And who promotes science on social media? Okay. So being active on social media or communicate science on social media, it's tough these days because of all the algorithms. But at the same time, and it's important to be present on social media, because for some people, social media, it's like a mirror of our society. And it's important to show science, because science is part of our life and it's really important. But your posts must be entertaining and attractive, because they compete with all the influencers, with all the animals, food bloggers and families. So think about that, but use the proper language. And you should choose different styles for different media. 2 years ago, I would recommend you Twitter, now X. These days, skip that. And my recommendation would be LinkedIn, Instagram, or YouTube if you want, if you like videos. And we can talk more about that in a discussion part. Go back to how. So that was social media. The next option is newsletter. And I have to mention Stanislav Foř and his great newsletter, Pokrok v AI. Yeah, so that's my recommendation. Subscribe if you aren't. The next option is traditional media, and it's really effective way how to reach a broad audience. For you, it might take like 30 minutes interview, and then the reach might be huge, and all the work is done by journalists. And for example, podcast, you don't need your own podcast. You might get the invitation. So think about that and think about the efficiency. And then there are events, like scientific conferences, events for the general public, and last but not least, events for policymakers and people from business. Again, in the Czech Republic, it's not well established, it's underestimated, but please think about that and focus on that, because it's really important, and we have to build the connection between the world of science and policymaking. So that, I guess that it was obvious, all these options, so I will give you some more unusual. Do you know the concept of one-pager? It's known from business. So it's like a summary on one page, summary of your project. For example, I use a one-pager when I applied for internship abroad because I wanted a control over my message, and I wanted something that it's easy to share. So my goal was share this, and that the PR department would put this one page into the coffee room, or that it's easy to share. So use it for your project. When you want to summarize something, it's great for networking. The other option is business card, and I don't mean the typical one with your contact details, but include like 1 or 2 sentences describing your projects, and via QR code you can upload your latest poster or publications and more details. And again, it's great for networking, because when you exchange business card and the next person find the business card next morning in a pocket, you increase the chance for future collaboration. Don't underestimate printed posters. It might work, especially when you organize an event at your university. So print posters and put them next to the elevator or close to the cafeteria, because not everybody reads emails or is on social media. So the old printed version might work. Various brand bags and what other items, it's questionable. It might work, might not. But remember, NASA or American startups, everybody has their t-shirt, brand t-shirt, and it's great for brand awareness. And last but not least, you might want to recycle your old fabric posters and create a dress or skirt, or have a t-shirt with your project. And that's strange, but it works for networking. And at big scientific conferences, it's tough, and it might be hard. When you are alone, it might be hard to start a conversation. When you wear something like that, I can guarantee that people will attract you, approach you, and you will start a cool conversation, and you never know who will meet. So think about it. It might work, and I really like that, and it's pretty common. So that's it. And now move to how to communicate science, practical tips. And let's be practical. So I have this example. Can you guess the topic of this article? Sorry? Yeah, it's molecular biology. And even I have background in clinical biochemistry, and I understand is, of, and that. So no worries. It's pretty complex, it's pretty detailed, but I was brave enough to write about or cover this publication in Hospodářské noviny, main Czech media for the general public. How to translate something so complex into the plain language. I wasn't able to use the biology because it would be like a big book and not one-page article. So I start with a story of a film editor, because everyone can imagine a film editor that he or she has, let's say, 3 hours raw recording. Then he or she creates a copy of it and edit the final, let's say, 1-minute video. And something similar is happening in our cells when we have DNA, a copy of RNA, and a final protein. So at the beginning, I started with this story of a film editor. In the second part, I shared what's new, what's the discovery, and I talk about more details. And somewhere here, I wrote one sentence that the team of David Staněk discovered a new helper of a film editor. In this sentence, I basically summarized the whole study. For scientists, it's brutal, I know, but for the general public, it was enough. It was the important knowledge that they had to learn. And in the rest of the article, because in the rest of the article, I had to explain why it's important and why it's a discovery, because it's pretty tough to find a new protein, a new helper. And it's important to know and understand all the mechanism, because if it's not working well, it causes diseases like blindness. And team of David Staněk, they study the mechanism and try to find a potential treatment. So to summarize, you have to find a story. It's good to use emotions, and you might want to use the weird story, like or weird stories, like that you made the biggest discovery by mistake, or that you made the most important discovery on Friday evening when you wanted to go for a holiday. It's great for journalists. And use examples and analogies from everyday life. For example, when Jan Černý, biologist, talked about the breakthrough success of AlphaFold, he used the analogy that it's like a moon landing. Because for the general public, they don't know, they don't understand what's AlphaFold and how big it's the revolution. So use similar analogies to explain your research. Then skip all the jargon and technical details, use plain language, and share just the minimal amount of information. In the whole article, I didn't use the words like spliceosome and all the RNA and mRNA proteins. I talk about protein and a new protein, and for the general public, it's enough. And for your colleagues, you wrote the original publication in the scientific article. And always think what's the most important and interesting for your target audience. I also covered this story for Charles University Magazine Forum, and I focus more on students. And I shared their story and their future plans and so on. But for Hospodářské noviny, we focus on the discovery and the future direction and future potential treatment. And prepare for the interview for the journalist. And I don't mean like have a nice dress or t-shirt, but think about all the analogies and the best explanations, because it increases the chance that you will be happy with the outcome. And science is beautiful, so show it. And these days, it's important to show beautiful images. Can you guess what's that? Yeah, it's the protein. It's the protein that David Staněk discovered. But for the general public, it's something weird. It's like a map of Africa or tangled mass. But from scientific point of view, that's exactly the protein. That's correct. In Hospodářské noviny, we use 1 microscopic images, like an example, And from scientific point of view, it's slightly wrong because it's just one example without any analysis, without any statistical analysis, or there is even no scale bar, for example. But it's beautiful, and for the general public, it's something fascinating. It's like an art. And if it's possible, show people, because science is made by people, so show it. And it's not just about group photos and profile picture. Be creative. For example, he is head of microbiology in Plzeň, and he's sitting on the floor in his lab. And it's weird, and it might be a great opening of your story. So be creative and compare the top and bottom line. It's the same place, just different angles with and without people. Can you see the difference? So think about that. Find a great producer and ask experts to do a good visual support of your science communication. Okay, so to summarize, to build a strong research brand, you need high quality research. It's the basic, and it's just a fact. Then you need a network. You have to know the right people, and networking is really a crucial skill for your future career. Then you have to communicate your research and talk about your successes and your projects. It's good to have a strategy, because then you are efficient and it's not time consuming. But usually it's a long-term process, and you need kind of consistency to communicate in a consistent way, and you have to be proactive and authentic. So summarize in a traditional way. Choose the way that you enjoy the most. There are many options that you can enjoy. Always keep in your mind who is your target audience. And according to your audience, choose the format and style. Use storytelling and analogies. Always explain the context and share just the minimal amount of information that are necessary for understanding. Look around for inspiration. You don't have to reinvent the wheel. So check your colleagues, check the top universities, how they communicate about your research, and get the inspiration. Better input means better output, so prepare for the interviews and don't create the opportunity for journalist creativity, let's say. Practice, practice, and practice, and ask for help. And if I can help you in any way, let me know. I will do my best to help you or connect you with my colleagues. I write 2 newsletters where I share your successes, new discoveries. So if I can help you or share your events or latest publication, let me know. Thank you very much.
Pavla is not going to be around for too long. She's got to run to another event. But do you have any question? One question for Pavla? Anybody?
So thanks for the lecture, for the talk. You talked a lot about the importance of knowing your target audience. I'm wondering, like in tech or in AI, there is I think a huge trend in writing things like Medium articles, which are usually serving as sort of tutorials, but they're usually not aimed at the general public. They're aimed at the other researchers, but they're written in a less formal way. Mm-hmm. But if you write this, then you probably do not have enough time or for so how do you choose to which target group to orient it?
It depends.
But, yeah.
It depends on your goal. If you want to exchange your knowledge with other scientists, then your articles might be great. But if you want to reach, let's say, future students, you have to use the language of the general public. So you might want to ask for help, like ask scientists or influencers that they can help you to communicate your research in like simpler way. And you can choose. It depends what you want to achieve. If you want to deliver your message to your colleagues or students or your grandma, let's say.
Maybe just adjusting the question a bit. So if you write it in a in a simpler way for the general public, do you have an experience that like the researchers would anyway read it, and anyway like those who want to look at the original article if they want? So it might be actually more important, right? Like to write it in a simpler way rather than the technical.
Yeah, because all scientists are people and they prefer communication in a simple and clear way. But it depends on the media, because not every scientist is on social media, and so it's hard to say. I have no evidence, but I know that my or that scientists read my articles. So they read about their colleagues. So it might be the good strategy.
Great, thank you. Thank you so much, Pavla.
Thank you.
Yay, pitching session. So as much as the conference is more about the soft topics, we still wanted you to gain some interesting insights into what's going on in the AI field in various labs across Prague. So we are very grateful to the 5 speakers who have been brave enough to sign up. I think that we have a hardcore dominance of the Faculty of Electronics from the Czech Technical University. All of them are from there. That's sending a great signal, I'm sure. And I would like to invite the first speaker, who is Jirka Němeček from the Center of Artificial Intelligence. The floor is yours.
Thank you. All right. Thank you very much. I was nervous before, but after the talk about how to do science communication, I'm even more nervous. I hope everything goes well. So, right. My talk will be, or my pitch will be about kind of my topic, or what I do in my PhD, which is integer optimization within artificial intelligence. And I would like to answer the question whether you should try it as well, maybe. So firstly, what is mixed integer linear optimization? So that's the very specific way to say it. I say usually MEO. I should probably stay here. So it's pretty much linear programming that you all know and love, with the exception that some of the variables are integers actually. So this little change makes it quite nice that we can actually formulate NP-hard tasks, which is great, and also since it's a global optimizing method, we can get pretty good results. Well, the best results, let's say. But the problem is that it tends to be computationally demanding. So, can MEO be used in AI? I would say yes, but there is a size limit. When the number of variables or integer variables becomes too large, say around 1 million, it tends to, so the solver tends to struggle. So we probably want either smaller models or less data when we consider the classic ML task. And this is actually not that big of a problem for what I'm trying to do, which is explainability. There we usually consider for interpretability we consider small models, and for explainability we sometimes don't need the data, we just need the model. So I'll briefly summarize my 2 works that I worked on. The first one is improving the usefulness of decision trees as explanations. Here we take a simple decision tree, as you all know. And we try to combat the problem that it often happens that once the tree becomes very accurate, actually what we see here is on the x-axis is the accuracy of the tree, and these dotted ones are for trees by themselves. And on the y-axis is the leaf accuracy, which is the accuracy of the worst performing leaf. So when we see that if we increase the accuracy, this is the best, let's say, model that we have. The leaf accuracy tends to drop. So we instead provided a different formulation that optimizes the leaf accuracy to improve the decision tree when we look at it as an explanation. Because when you are a person and you're classified by a tree, and you get some path through the tree, and that's the explanation. It's like, because you're this old and this high, you are classified as this class C. You would like imagine that this is a pretty good explanation, but it might be the case that the explanation has actually pretty much like a 50-50 chance of being incorrect, which is like useless explanation pretty much. Right. So this was I would say a good application for the mixed integer optimization, because we are explaining trees that are meant, we're optimizing trees that are meant as explanations, which means that they are small, and then we could use, let's say, reasonable amount of data around 10K points. The other topic is, the other work is on generating likely counterfactuals using sum product networks, which might be a lot at first, but let's break it down. Counterfactuals are counterfactual explanations, which is sort of the same thing as adversarial examples, which you might know. So it's like the minimal change you need to do to an input to change the output of the model. Right, but we want them, the adversarial examples, if you think about them, they're usually like, they still seem like the first class, right? But you want, like the counterfactual explanation should be more like explaining, should represent something that's actually truly from the distribution of the class that you're trying to move to. Right, I'll speed up. So that you can improve by implementing it, like by estimating its likelihood, which we do through sum product networks, which was the main contribution. What I show here is that we get a 100% retrieval rate, let's say, of the explanation, which is not true for other methods. This is the case because it's like the method is exact, so we are sure to find a solution when we have the time. That's the last line. All right, and this thing is the same project. I only show that the global optimality is a great thing because you beat everybody else. And yeah, for this one, we didn't need any data, so also great for integer optimization. Well, great, whatever, great. And we can use reasonably sized models because we don't have the data. Right, that's about it. If you have any questions or advice or anything, you want to talk to me, I have also some posters in the back. Feel free. Thank you.
Thank you. It's fine. And the next in line is Marek Miltner, also from CTU. The stage is yours.
Awesome. Just like my previous speaker, by the way, amazing presentation. I don't know where he disappeared, but oh, there you are. Amazing presentation. I also have a massive imposter syndrome standing here because this is a loaded topic, right? Like AI, everyone is working on AI, and everyone is accusing each other of not understanding what AI is. So I'm definitely still in the camp of not understanding the full breadth of AI, but doing my best. And what I'm going to talk about is something related to AI and sustainability. And I was told we have a little bit more time than expected, so I might as well tell you a little bit of my personal background. So I was born in 1996 in Prague, which is not relevant, but I spent the first part of my career working after graduating CTU and then Cambridge in industry, working on some startups, had a cushy job in AI. And then I had this kind of existential crisis where I felt like, I was just chasing kind of commercial goals, be it in a startup or in corporate field or in consulting or whatever. And I wanted to contribute to the world. And I remembered from some of my lectures when, be it at the electrical faculty here or in Cambridge, where the vast majority of climate change, of course, caused by CO2 emissions, can be attributed to energy. And from the electrical faculty, I knew a thing or two about that. So I went back to academia, trying to finish a PhD here, started this beautiful collaboration with Stanford. And now with that, we're trying to also increase our collaboration by founding a lab here at CTU in Prague with a deep collaboration with Stanford called LIMES. So hopefully you'll hear more and more about that. But back to, and I love limes, the fruit, so that's part of the reason. But now let's look at generatively modeling European public EV charging behavior. Okay, motivation and context. So electric vehicles are more and more common. Even in Prague, you might see a Tesla. And with them comes a demand for chargers and charging itself. However, infrastructure for charging is not easy or quick to build. Whereas for the cars themselves, you get this economy of scale where with more demand, more cars, you get a lower price, right? You can see the lower price of batteries and it's becoming more accessible. The Chinese are especially good at this, right? The cars they're producing there are becoming very, very accessible, even cheaper than combustion cars. And so, this trend can continue exponentially for a long time. However, for the charging infrastructure, you do not have this kind of economic mechanic, right? When you're a distributor, let's say a distribution systems operator, you are more likely to start building chargers where you have space, you have free capacity in the cables, in the substations, and et cetera. And then you go to the more difficult places, and at a certain point, you just have to slow down, right? So this is why it's important, and maybe coming back to that point, when you want to expand capacity somewhere, that's a big project, right? It's not just Elon Musk putting at a point of ground, I want a charger here, but you might need tens, hundreds, thousands of chargers, and for that you need to upgrade substations, the cables under the beautiful pavements in central Prague. You need to have all these permits from the architectural committees, and that takes time, right? It can take several years. So for that reason, we need to better understand and characterize the charging of electric vehicles to build infrastructure more efficiently. To detect systemic challenges in capacity, like where that will happen, when it will happen, and utilize EV charging potential for grid balancing, or just in general, use the infrastructure we have in the most efficient way. That's what we've been trying to do. And to illustrate this point, this is real data from Czechia, by the way. The blue bars are the count of EVs, and you can see that's pretty exponential. But for the red line, which is the charging points, you can see a slight slowdown between 2020 and 2021. So this is not like deep research, but just anecdotally, it seems like this kind of slowdown might already be happening. I also want to acknowledge my friend and colleague from Stanford, Shravan Powell, whose work I'm building on. So she has been the first in the world, really, to characterize public charging in California and compared it with private charging, where for private charging, which is prevalent in the US, you have this horrible, horrible peak where everyone basically finishes work at 5 p.m., comes home at 6 p.m., plugs their EV charge in, and you get this surge in demand, which is crazy, super expensive for the grid, and you get frequent blackouts in California. Not so much in Prague, and she's basically shown that with public charging, where you have this load over during the day, you can counterbalance that. So what we're trying to say, or what we were trying to show, is can we see the same thing in Prague, for example, or in Europe wider, and can we gain perhaps an even better understanding? So we used a bunch of different data sets. We worked with the largest systems operator in Prague, and we used some demographic information from the statistical office, population dynamics. We had all these different data points. It was so fun connecting that. And essentially, we had to work with a dilemma that every scientist, I guess, has to encounter every now and then, where some of the data we couldn't really make public because there was some private information or business-specific information that predistributor didn't want to share. So we had to label it and sanitize it. And we essentially did two things. One is this generalized charging behavior assessment, so understanding what charging looks like today. And then we created this model with which we can play around, right? We can tweak its inputs to understand two things, really. How would a public EV charger work, or what would the behavior of charging of real people charging their EVs there look like in a place where there's no chargers today, which is very interesting. And then what will it look like in 10, 20 years where there's 10, 20 times the EVs, so that we can identify where the system might overload because of cables or substations, or you said. So this is like a showcase of how many chargers are in Prague and different parts of Prague, because we split Prague into basic administrative units. There's about 1,000 units that's been defined by the statistical office. And we map that onto these types of areas. What's great about these types is that they are not AI generated. Those are connected to how the statistical office defines these, and they actually inform what can be built in these places. So they are a great input. And so you have some residential areas more in the center. Then you have some transport areas, for example, industrial areas. Mixed areas are also commercial. And then at the edges, you have some agricultural areas. I was very surprised to see in Prague. And we even have a forest area. Who would have known? But let's go to the results. So one of the interesting things that we saw is that for the initial data set that we worked with, which was between 2020 and 2022, some types of areas are being used more than you would expect by the number of chargers, right? So at the bottom, you have the share of chargers within each type of area. And at the top, you have a share of chargers, or a share of charging sessions, right? So on the top is how much is being charged in the areas. At the bottom is how many actual chargers are there. And you can see that in, for example, the civic amenities area, it's being charged way more than there are chargers, or not way more, but significantly more. But for example, for the recreational areas, that's a significant part of chargers here, but we don't get that many charging sessions. So that was the first very interesting thing. So somewhere we are building more chargers than we need, and some we might need more chargers than we have. And then the first kind of breakthrough that we've showcased came last year, where we've shown that based on where you put the charger, you get a different profile. We saw 4 distinct groups of load shapes, which is what the distribution systems operators care about. And this has never been really shown before. So the first group is what we've seen in California as well, right? Where you have a large population center in the center, be it residential or mixed with commercial and civic amenities area. You had this beautiful, load curve throughout the day. But when you look at the separated residential areas and the agricultural areas, so near the edge of town, kind of close to suburbia, closer to what you might expect in California, you get this, still it's during the day, but you have an evening peak. So it's closer to what you would expect from a private charger, for example. Very different still from the third group, the transportation infrastructure areas and recreational areas, for whatever reason, who have a clear morning peak, right? The transportation infrastructure, which is basically the airport, has it around 10 a.m., the recreational around 8. but it's different. And the industrial or reserve areas, which is the fourth group, they have, you know, a more random kind of pattern, but they have multiple peaks during the day. That's been very, very interesting. We've been the first one to kind of document this. And then what we've done is, can we extract some sort of generalized insight about this? So we've created a neural network, because we're doing AI, of course, and we've done a custom architecture. And the custom architecture works like this. We have essentially assumed that there are, since we have 4 distinct groups of behavior that we've seen in the on the real data, we have assumed that there's 4 distinct patterns of behavior that are underlying each part, you know, that are that every charger is kind of consisted of, right? So we're training these latent load profiles that the neural net is supposed to learn, and then we're also training for each charger the ratio between these 4 load profiles, right? And then the DSOs, what they're interested in is not just the load shape, but also the peak load, right? How much power we will need at a certain point. And so for that, we also have created a different module, and basically that just predicts a number, and if we multiply the number by the shape, we get, you know, the load curve that we're expecting. And the good news is, of course, the loss function here shows that the network is trained on the data, and it kind of understands the, or is able to generalize the behavior. But also the big kind of breakthrough is the latent curves. If our assumption was correct, that the 4 behaviors would be there, they would somewhat reflect the 4 behaviors we've seen in the previous slide. And this is exactly what happened, right? So in the latent curve number 1 kind of corresponds to the behavior of charging during the day. Latent curve number 2 has a peak in the morning. Latent curve number 3 has a peak in the evening. And the number 4 is kind of the rest. Right, so this has been very cool, and I'm happy to say that we've this kind of insight has been accepted to a workshop at NeurIPS. So that's going to be presented at one of the prominent AI conferences end of this year, and brings me to my conclusion. Number 1, location of public EV chargers greatly affects their load curve shapes during the day. Number 2, we can use generative AI to reliably predict EV load curves, even in locations where EV chargers are not yet present. And number 3, this can efficiently help distribution systems operators in planning infrastructure expansion, which is a very, very complicated problem. And with that, I thank you for your attention, and I look forward to the next speakers.
I've turned out to be a very bad timekeeper, so I'm going to ask the remaining speakers, starting with Tomáš Musil, to keep it short and sweet. Thank you. But I'm loving the passion, of course.
Thank you. Yeah, I was not planning on keeping it short and sweet, but here we go. Those are... How does this... Can someone... Huh? What? There. Ah, yes. Okay, thank you. Still... Ah, good. Okay, I was doing the same thing, but okay. All right, so those were some very nice talks from people who have done a lot of research and know their research topic. That is not my case. I'm just now beginning my PhD at the Multi-Robot Systems Group led by Martin Saska, and I will be talking about I'm just preparing or formulating the research questions that I want to focus on, so I will be talking about some interesting research and some questions that are still a work in progress. So the main topic I want to focus on is mapping and navigating unknown environments. So imagine you are a firefighter and you need to save someone in a building which you have never seen. You need to quickly go inside, build a mental map of where things are, and use that to navigate. This was recently done basically in the DARPA Subterranean Challenge in robotics. the state, well, the state of robotics right now is that they can build maps kind of quickly during one mission on a scale of roughly like 1 square kilometer. You could say, yes, this is solved, SLAM is solved, but these approaches are fragile and can break. Compare this to animals. Egyptian fruit bats can, if you take a fruit bat, you put it in a box, you kidnap it, you transport it 40 kilometers away, and you release it, it will navigate reliably back to its cave, which you can see in this part, over like 40 kilometers. So this suggests that they have some internal map, which is like 50 by 50 kilometers square. This is unlike anything in robotics right now. So how do they do this? Well, there's actually a lot of research on building cognitive maps for spatial navigation. Okay, short and sweet. There are some cells, for example, researchers discovered cells which, neurons in the hippocampus, which fire only in some specific area. So one cell, for example, fires in this corner, a different place cell, they are called place cells, fires in a different corner and stuff like that. They also discovered cells that encode like structural qualities. For example, there are grid cell neurons which fire in a repeating pattern as the mouse is moving around, and they are thought to be like the coordinate system of rats and mammals. Border cells, direction cells, they also encode, like, border cells fire near specific walls, head direction cells like are basically the compass. And yes, you might think, yeah, this is just spatial navigation, and yeah, hippocampus is useful for that. Okay, but what's striking to me is that these cells are used to create maps of abstract spaces as well. For example, there was an experiment where there is a mouse. It is tasked to hold a lever. Oh, it's hearing a frequency. If it presses on the lever, the frequency increases, and its task is to like move the frequency that it's hearing to some target zone, and then it gets some food. And what researchers found was that they discovered in the same area where you have place cells, they discovered something that they called frequency cells. So, for example, one cell fires when it's here, and the mouse is hearing a low frequency, and then a different here, then a different here, a different cell here. So it's basically creating a frequency map of the task, which is interesting. But so these place cells or the hippocampal cells are not just for mapping space, but any like task space. Also, there are different cells, splitter cells. For example, these are place cells which fire based on the context of what the rat is doing. If it was tasked to run in this way, like from the left, down, and up, the cell was firing in like the corridor, in the middle corridor. But when it was moving through the same space, but in a different context, the cell did not fire. So there are hundreds, or not hundreds, like tens of these very specific neurons in the hippocampus and entorhinal cortex. Also, there is evidence of this in humans. They were trying to move through bird space, which they were seeing birds, and their task was to form the birds into some particular shape by extending their legs or their necks using two levers. So you can like imagine this as morphing these birds in 2 dimensions or moving through a 2-dimensional bird space. And researchers found encoding using EEG, which is very similar to the grid cell. So this suggests that the brain is projecting the problem into 2 dimensions. So it's not just for navigating physical space, these cells. Okay, so this brings me to the 2 research directions that I think could stem from this. First is like there's a lot more interesting qualities of these entorhinal hippocampal cells, which I didn't have time to talk about, but the first direction I think would be taking the findings about these cells and improving how we do robotics, how we do these handcrafted approaches to how robots create their maps. So we could just see how the brain is doing and handcraft that, hard code this, which is usually done in robotics. mostly to improve SLAM, simultaneous localization and mapping. But also, I think it would be very interesting to focus on, well, it's not a new idea, but to focus on creating systems where these grid cells, place cells, frequency cells, splitter cells, and others emerge, and where they are reused also for some other task. For example, there has been research done by DeepMind, it's the image on the right, where they used LSTMs and some other stuff. And the task was to navigate to some specific area in a simulated world. And something like grid cells emerged in the codings of the LSTM, which is very interesting. Also, there was research on the Tolman-Eichenbaum machine, that is the image on the bottom, which is trying to replicate the hippocampus and entorhinal cortex. And that works kind of well. Also, like the other types of cells, these border cells, grid cells, place cells, and also other types which were important to the task at hand emerged. And funny, interesting thing is, if you take the output of the Tolman-Eichenbaum machine and you add softmax, you get a transformer, which is, I guess, interesting. I don't know what to make of it, but I find it highly interesting. But they are slow. For example, when a rat goes to a new environment, some place cells emerge instantly. You can instantly identify a cell that starts firing in some specific place. But here it takes like many iterations. So what I'm trying to say, I guess, is that the hippocampus and entorhinal cortex, which are like creating the context and updating the context about the task. And it's somehow automatically like creating all these splitter cells, place cells, that's what is important for the task at hand. So it would be interesting to explore this further. I hope that wasn't too chaotic. I guess you're looking at me now to end. So yeah, that will be all by me. These are the references. And I would love to hear your feedback on these ideas and to meet anyone who's also interested in these topics. Thank you.
Thank you. I've been looking at you for most of it. It sounded very sweet indeed. The next speaker is Daniel Alcides Saramono More, also from CIIRC CTU.
Thank you. And for the pointer?
Pointer, that's a good question. Try, I don't know.
Or maybe
I'm not too sure if pointer
this.
is. Well done.
Okay, okay.
Yeah,
Thank you. Please raise your hands. Anyone here who has ever done, like, trained a transformer architecture, like attention layers, that kind of stuff. Okay, transformer. Okay, nice. Let's go now with a recurrent layer. Who has ever trained a recurrent neural network? Recurrent, LSTM, GRU. Okay, nice. Convolutional. Sorry, a spoiler. Convolutional layer. Who has ever trained a convolutional layer? Nice. And the multi-layer perceptron, the classical, dense, fully connected. Okay. What do all of these layers types have in common? Maybe like you have used an implementation in Python, who knows, or in Lua. There are some crazy people working in Lua. Or specifically, maybe you have used Keras or TensorFlow or PyTorch. But what if we go deeper into the mathematical concept? What all of these layers share, actually, in the behind the scenes, they work in some way or another, they work with the dot product, okay? So we have the perceptron, invented by McCulloch-Zapitz in 1945, I think, and then improved by Dr. Rosenblatt in her famous thesis. But there's a situation, okay? I'm going to analyze the dot product in the simplest layer that uses this operation, that is like the dense layer, so here's a perceptron, okay? When we train a neural network, we all know that we use the derivatives because the backpropagation technique is the most useful method to train neural networks. But what happens if during the training, our neurons are outside this gray area? If the neurons have very low derivatives, we enter into a zone with low gradients. And this is the so-called the vanishing gradient problem. If we have very low gradients when we train neural networks, the neural network does not learn very well. So there's a thing, like we have, okay, the perceptron, okay, that on the behind the scenes, it has like, in this part, is the dot product, okay, and then the nonlinear activation. But what if there could be a way in which, okay, by design, the perceptron, the new dot product, can make us work only in this gray area that I call the dynamic region. And also, okay, we can do it, okay, but is it useful? And also, can we extrapolate that to not only dense layers, but maybe convolutional, transformer, or recurrent? Is it possible? Hello, my name is Daniel Saromo. I am from the Amazon forest parts of Peru. I am very cold right now, okay? And I'm here to present you my research, which is called the auto-rotating neural networks. It's a research done in collaboration with the University of Groningen with the professor Matías Valdenegro Toro. Okay, I invented these neurons in 2019, and I had the opportunity to present in a workshop at the NeurIPS in Vancouver. And in that first version, I presented this kind of a structure. I have I have two neural networks: the classical perceptrons and my auto-rotating perceptrons. So if we train them, okay, like the classical is the red. Let's focus on this graph. The higher value is the better. If we train the neural network, the classical neural network, we have this learning curve. Okay, if we have the same neural network, the same initial weight, but we change to auto-rotating neural networks, we have this graph. So there's a very interesting improvement on the learning performance when we just change from classical dot product to auto-rotating dot product. Okay, but someone could say, okay, this is a simple neural network. Okay. And you're just taking with dense layers. Like, is it possible to do it like beyond dense layers? I don't know. And also someone could say, but okay, you have used, you want to change the dot product, but is it the only way? Like, what are the current techniques that people use in order to tackle the vanishing gradient problem? One of the most famous techniques to do so is the famous batch normalization. So what I did in this experiment is I took 4 neural networks, okay, and I put all the combination without and with batch normalization and without and with the auto-rotation. And I have here these graphs. I don't have like too much time for deeper into the mathematical details, but for example, like the classical without batch normalization and without auto-rotation is this curve in red. It's not that good. It's the worst of all of them. The classical approach, okay, you have no auto-rotation and batch normalization. We have that the learning curve is a bit bumpy. With my approach, that is colored in green, we have that the curve is above all of them and is much more stable than all the other ones, which is interesting. But okay, we have the learning curves, okay, but like technically you wanted to tackle the vanishing gradient problem. You wanted to avoid the low gradients. This is the graph that analyzes some gradients in neural networks. For example, here is the vanilla model. You don't have batch normalization and you don't have auto-rotation. The models on the left are the model without auto-rotation. When I change from here to here, I mean from nothing, no batch normalization and no auto-rotation, and when changing from here to here, we see, okay, there are less lower values, like this yellow zone. Look at the legend of the bar, on the bar there. This yellow zone kind of disappear, and there are no blue zones. Okay, with the current approach, with batch normalization, we technically avoid some vanishing gradients. It's okay. But what if we have this neural network and we apply just the auto-rotation? Look at this nice color. Look at this. So it's like we avoid, technically, it's much better than doing the batch normalization itself. Okay, but we still have some problems here in the beginning. Look, there are some low gradients that we don't want. But what if we take together the batch normalization and the auto-rotation? And here are the results. It's like we see that it's much more uniform because the speed of learning is kind of similar across the layers, and it's more stable because across the epoch there's not too much variations. Like here, for example, it's not that very stable, and it's also not that uniform. So, like, this is I know very few things about artificial intelligence, and I wanted to share with you a bit of my research, and like, I'm open to any comments. I know I'm open to any feedback, and thank you for your attention. I'm happy to be here. Take care.
Thank you so much, Daniel. I think you've set the benchmark for presentation style pretty high. Loving the passion and energy. The last but not least, Please let's welcome David Fiedler, who is one of the freshest PhD graduates we have on the block, also from FILE.
Yeah, thank you for welcome. Let's try that magical button. Oh, it works. So I'm pretty nervous because my presentation is not about what I've done, but instead is what I want to do. So it's much more basic than the previous presentation, presentations, I believe. So let's go for it. So my idea, what to do next, is about how to integrate mobility on-demand systems into designing transportation networks for mass transportation, basically for public transport. So the idea is that instead of people transported by private vehicles, which is the left image, we will use mobility on-demand systems to transport the same amount of people in less vehicles and hopefully even like travel less, basically that the total travel distance is lower. In the bottom image, you can see the classical taxi service or Uber or something like that. Basically, we serve the passengers in sequence, while in the top there is ride sharing. So there are multiple people transported in the same vehicle at the same time. And the idea about integrating mobility on demand into mass transit is that there are areas with high travel demand that can be serviced by the mass transportation, and areas with lower demand where we can use mobility on demand systems for first mile, last mile transportation. Now, the network design problem, even just for the mass transit, is really complex because there are countless of options how to do that. We have a lot of options how to design the lines. We have a lot of options where to put our stations, and also the frequencies can vary. And the goal of like what we want to achieve by solving the network design problem is that we want to serve, we want to maximize the number of requests that will be served. Ideally, we want to transport everyone, and at the same time, we want to minimize the travel time. Now, the idea, which is not still not mine, but the idea which is currently popular in transportation literature is that we can use mobility on-demand systems to supplement transportation in low-demand areas. And the problem of this, but the problem of the research in this area is that currently this idea is only explored, only studied on the operational level. Yeah, so we take an existing transportation network and we plan how to operate the on-demand vehicles so that it supplements the existing bus lines, existing subway lines, existing tram lines. And what I want to, sorry. So, and how is that done? Usually, there is some kind of iterative meta-heuristic used that works from some starting solution, then the solution cost is computed, then we basically decide whether the solution cost is better than the previous solution, and if it is the case, we update the best solution. And finally, we try to improve the solution, and we cycle. This is like a lot of iteration of this cycle, hundreds of thousands of these iterations. And at the end, hopefully, we have a good transportation network. And my idea is basically how we can modify this process. So instead of just exploring the operational level, we can consider mobility on demand in the designing process. And my idea, or the methodology I want to use, but maybe it's naive, but let's talk about that. So what I want to use is the fact that all of these methods that are used to design the transportation networks, and this does not include only meta-heuristics, but even machine learning approaches and integer linear program methods, is that all of these methods have some component when the solution cost is computed. And I think that we mostly have to modify only this part. So first, we allow, in the design of the network, we allow part of the demand not to be served by the mass transportation. We allow solutions, lines that set of lines that does not cover the whole demand. And then we modify the solution cost computation so that instead of the current solution, which only computes for each request, it computes the shortest path in the transportation network. We allow people also to be transported by the mobility on demand system. This, of course, change the problem of computing the solution cost drastically, because instead of a shortest path problem, it becomes a dial a ride problem, which is much harder. Yeah, so here we go for the challenges of this approach. The complexity of computing the cost is much harder with the proposed solution, and also there is another complexity which stems from the fact that we have to design, we have to decide where we allow people to change from public transportation to mobility on demand and vice versa, because when we consider all the points, when we, for example, allow all stops as transfer points, the problem gets even more complex. Yeah, so we have to limit this somehow. So thank you for your attention, and yeah, please find me if you see any pitfall or problem with my approach, because this is certainly the case. So don't hesitate to stop me now. It's better to not invest time into something that is hopeless. Yes. So thank you.
Thank you, David. We have one last speaker. I know that you've been sitting for quite a while, but I'm sure he's going to be fantastic. When we were looking for the right speaker for this particular topic, maximizing internship abroad, again, it wasn't a very hard mission. I would like to invite Will Olissi from CIIRC CTU, who is an associate professor there, and I don't know how he's going to introduce himself, but he's a great speaker for many topics, from game theory to many others, but for this one as well, as he was a visiting scholar in Israel, the US, and he spent 2 years on his postdoc in Canada, which was, I suppose, part of his mission with deep stack algorithm. The floor is yours.
Thank you very much. So we are running late. Do I still have half an hour, or how do I do it? Okay. And maybe I'll just take notes, because I expected to have a break in between. Perfect. Okay, so I didn't have this presentation prepared. I was just approached to give it, so I was thinking for a bit how to approach it. And I'll just have the standard dance. It's not doing anything. It's pointing, but okay. So I eventually decided to just tell you part of my story, not because it would be somehow particularly noteworthy, but because I can use it to demonstrate very precise, practical things I did that worked for me and that you might consider doing in your path as well. And it will be all about like international experience. And when I was thinking about it, I always thought that I was just super lucky, right? Like my research career, at least, was going very smoothly, and I got all these great opportunities that helped me to like see great things and do great things. And it was plenty of luck. But on the other hand, I think many people have all sorts of opportunities coming to them, and you really have to be open to getting lucky, right? You have to try things, you have to apply for things, and when things are going around, you have to be brave enough to take them and to go for them. So these random events started already with me being here in Prague. So originally I'm from Slovakia, from Bratislava, and one of these random events was that I was just like shopping with my mom, and she took me to a bookshop, and I didn't care about books. I was finishing my high school, and I was thinking what to do for my university. So I just saw this particular but a similar book in the bookshop and started browsing, and I saw that, okay, there is a mathematics and physics faculty in Prague, and they would just take me without acceptance exam. And I was scared that I wouldn't get accepted into Bratislava, into the mathematics and physics, because it was very hard school. So I just applied just to be sure, right? Like, if I don't get accepted in Bratislava, I'll just go to Prague. And then during the summer, I was thinking about that, like, yeah, I got accepted to both. But then I was thinking about what to do. And then, like, if I stayed in Bratislava, I would be living at home with my parents for the next 5 years. Like, it wouldn't be so much fun. It wouldn't be adventure. So eventually I decided to take this plan B and go to Prague and to experience new things. And it was a very important. I think like most of the things that I'll be talking about today would not happen without this kind of leap of faith to do something adventurous. So I ended up in Prague at the Faculty of Mathematics and Physics, which was great. I was learning a lot of things, met a lot of friends, and I was drinking a lot of tea. And when we were sitting in a dorm room, I remember it very well, with a group of friends, we were just chatting, and one of them told me that there is this opportunity of going for a master program abroad into Amsterdam, and there is a stipend with it. So I wouldn't really have to pay for it, and it would be paid for. And yeah, he just heard about it. Conversation went on. But I remembered this, and then later I digged in, and I found out that, yeah, there is this program. It's not too difficult to apply. I did apply, and maybe you know, maybe you don't know, Czechs are not super eager to go for these things, so it wasn't that hard to get it. And then I ended up in Amsterdam for a year at Free University of Amsterdam, which was great experience. Like, even with me moving from Slovakia to Prague, like, it was moving abroad, but still, like, the culture is very similar, the language is very similar, everything works kind of similar, and this was a great, like, learning experience. I was living in an international guest house with 200 people from all over the world, like working during the days, partying every night. And it was really interesting from the personal perspective. I was really on my own. I had to take care of everything, of like bank account, of ID, of all these things that you wouldn't have to do. And I saw how research is done at different places, right? I saw that my post-Soviet education was pretty good. That actually, like compared to the other colleagues there, I was really good at math. I knew most of the things that they were trying to teach me, and it was rather easy to excel. What is the lesson learned here, in my opinion, is that it's actually quite common that better universities or more famous universities are trying to drain brains from the weaker universities, and they have all sorts of scholarship programs. It's not only Erasmus. There are like tens of these programs where if you are looking around, if you are interested, you can probably get in. You can get paid in scholarships. It doesn't have to be expensive, and you should really consider it and try to do it. Then, yeah, we are not just partying. There was some learning as well. And I took this course, which wasn't super interesting. It was called Behavior Dynamics. It was about AI and logics and behaviors and whatever combined together. And I was diligent. I did my homeworks. I was working quite well. And I was kind of building relationship with the teacher who was teaching it. And it's actually paid off eventually, because he remembered me from the classes. He knew that I'm kind of, I can do my work. And when I was to choose my master thesis, I just went to him and talked to him about it. And I figured out that he's actually working part-time for Philips. He has interesting projects there. And I started working on a project on emotion recognition using neural networks in 2005, it was pretty interesting. I saw for the first time how industrial research looks like in Philips, like a huge multinational corporation. What it's like takes. I was like building some connections there, and like one of the things that was pretty interesting for me is that I was all about hard work at that time. And in my final evaluation after the internship at Philips, the only complaint that was there was that I was working too much, that I didn't spend enough time like socializing at the coffee machine, like talking to the colleagues. And like at that point, I didn't think it's really important. But as the previous speaker was talking about, like, networking is super important. Now I'll get back to it during this talk several times. Like, you should socialize more. But there are again couple of takeaways here. I think when you are thinking like for your master's or even PhD courses, I always advise my students to look at teachers much more than the subjects. Like, the subjects can be okay, you will learn something, you will train your brain. Most likely you will not use that specific knowledge. But if you find interesting people who are doing interesting things, you build a relationship with them, then they can advance your careers much more than the specific like neural network architecture or whatever you learn in that class. So really try to focus more on the people than just on the subjects that you are interested in. Work hard, like show that you are good. If you are good, don't slack. Then like the teachers will happily find some time for you, like a half an hour to advise you with your career, to like introduce you somewhere, search for internships at the companies. Like, all these options are there. You just have to search for them. Okay, so that was Amsterdam. I got an offer to stay there for PhD, but I didn't enjoy it there for several reasons, which I'll not go too much into. We can talk about that later. But then I was like decided that I want to do PhD, and I was thinking where to go. So how do I approach it? I was searching online for, again, people who are doing interesting things, for groups at that point more, because I didn't know the people that are doing interesting things. And I found out about this University of Edinburgh, which I've heard is pretty good for AI. I knew that I want to do AI, and I found a professor there who seemed interesting. We like chatted a lot, and then he offered me the position. It was great, so I was happy. I thought that I'm going to Edinburgh. And then communication was getting slower and slower and slower, and then at some point it happened that I found out that like he didn't get the funding that he hoped for, and that he will not have the money to pay me, and that like I will probably not be able to go there, which was sad. But then like I had to take some other opportunity, which was kind of plan B here in Prague, to go for Czech Technical University. And this plan B actually worked pretty well as well. So two learnings from this. One is try to keep much more options open. Like even if one looks very, very good, it's worthwhile to spend time to create several other backup plans, but then even the backup plans can actually work out pretty well. So I started to work in something that was at that time called Agent Technology Group, and we were doing mainly like flashy demos for defense projects because like the research wasn't that great yet, but we were, among other things, interested in like multi UAV scenarios where we were doing some coordination like tracking targets or surveillance and these things. And we had a couple of projects with US defense agencies, which was like great work of my advisor, Michal Piechowczak. And we also had one project funded by a Ministry of Education, which was for collaboration. Like there are these projects very often which are just pushing the scientists to do collaborations with others, because initially it's work, people don't like it, but at the end when people are looking back to it, everybody thinks it's a great idea and it's great, but like they need this little push. And Michal had this like good relationship with Katja Sikara, who was a professor at Carnegie Mellon University, and so we had this shared project, and as a part of that project, we had like 2 half-year-long trips to Carnegie Mellon University, which is like one of the 2 top technical universities, and we were working on projects together with them, and it was an amazing experience. It was a completely different world, mainly from understanding that all the celebrity researchers are just people, and all the huge kind of projects that you read in newspapers are just projects of people who decided to try to do this. Like you just normalizes ambitions so much that all the people like Tom Mitchell or whatever, like people who I was reading books from when I was learning, I thought that all of these people are somewhere in the clouds, like doing the great research for the world. And then they just had offices across the corridor, right? They were coming to the same seminars as I was coming, and they were like asking the same stupid questions sometimes, didn't understand things that I did understand. And it was very kind of encouraging to see that all these people from the posters are just approachable, and I can work with them. And thinking that I can build the first algorithm that can beat best people in poker is just a regular project to start working on, is something which I wouldn't think about before. And this environment of Nobel laureates speaking every week, and like the keynote speakers from top conferences just coming around for lunch was very, very inspiring in this. So again, if I were to distill it to a couple of lessons learned, network of advisors is super important. Like this was again enabled by that. So if you are picking an advisor, think about that as well. Like who are his collaborators or her collaborators who you might be collaborating with. And if you are hoping to become advisors at some point, work on networking, work on having interesting collaborators where you can send students, where you can like get some students and so on. So networking is super important. Ambitions are just normals, are as normal, and you should really aim very, very high. And this environment just teaches it well. And also, it was interesting to see the quality of the peers, of the students, of the teachers. So I would summarize it like the top of the top are probably rather similar. It's not like they are some amazingly like 100 times more intelligent people than you have here. but then the spread is much higher. Like even the worst student, the worst professor there is probably much better than the average here. So it's worth going there because whoever you collaborate with, it's very likely that they will able to push you somewhere further and they will try to help you, teach you a lot, right? And another thing that I realized is that there is a really big domino effect. Like once you start somewhere, once you get to this great place, you start collaborating with the great people, new opportunities just come up and follow from that. So for example, in the half a year I spent at CMU, I was collaborating with Roy Zivan, who was a postdoc there, and then afterwards he came back to Israel, where he was from, got a professor position at the university. So he got some grants. In that grants, he again had some money for international collaboration, whatever. He needed to spend the money. He didn't know too many like good people who are doing similar things that he's doing. So he asked me whether like I wouldn't be able to come for a month to Israel. He paid for everything. He introduced me to his great students who took me to trips to Black Sea and Jerusalem and everything. And it was like great experience personally. But again, I learned a lot about how the organization works. I get to know a couple of people that's like I was collaborating later and so on. Similarly, at CMU, I met Bo An, who was like just interviewing there, but we were talking a lot during the interviews. He didn't get the position at the end. He went somewhere else, but we kept in touch and kept meeting at the conferences. And now he's a full professor at Nanyang University in Singapore. And I've already kind of sent his direction to students who were working with me before. One of them has already finished the PhD with them. Another one is still working there. So the two things are that there is this domino effect. Once you get to some interesting places, collaborate with some interesting people, like more and more opportunities will just start appearing. And researchers are just people, really. Not only that you shouldn't be afraid to approach them, but also they like to collaborate with their friends, right? Like once they know you, like if they have an interesting opportunity, like why would they search all over the internet to find somebody who can fill it if they can just write you and ask whether you can fill it, right? If they want to cite a paper that somebody wrote and they like talk to you about the paper, then it's more likely that they will actually cite your paper, even if it's not the best paper ever, but they just know you and it's nothing bad about that. It just works this way and it's good to realize it and to just work on that. Okay, so this was like pretty much in the middle of my PhD, but towards the end of my PhD, I was kind of wrapping up the dissertation. I already knew what I wanted to do. I read all the papers. And one thing which I think is really important to do is to try to understand who are the key people in the field you are interested in. Like they start appearing on the best papers that you read. And towards the end of the dissertation, like my vision was to combine kind of these two works. One was about Monte Carlo research, which probably now after AlphaGo and so everybody knows. But even back then, it was kind of an interesting algorithm that was beating benchmarks in many fields. And Monte Carlo counterfactual regret minimization algorithm by Mark Langto from Michael Bowling's group. And Michael Bowling was one of these people who I always saw on the best papers, right? Like when I saw really great paper that I liked, it's again from his group, and it's again from his group. So this is how I kind of understood a couple of people who were really good, who I would like to work with. And since I wanted to combine these two papers, I started talking to Mark Langto about like details of that paper, and he got also interested in this idea of combining, like doing something like Monte Carlo research, but for imperfect information games. And he didn't have time to work on it because he was already like a little more advanced in the career, but he was happy to like help me, to coach me, to guide me. And even before finishing my PhD, I managed to write a paper with Mark and Michael Bowling that was on topic of combining these things. It wasn't like a great paper, it was okay paper, accepted at a very good conference. But it really, again, opened the door to further collaboration with these people. So then I submitted my PhD, and I was thinking about postdoc, like where to go. And I was at CIIRC conference, one of the premier AI conferences, and I already knew Mike Bowling because we wrote the paper together. So I approached him, I talked to him quite a lot about like what he's planning and what I'm planning and so on. And then there was a board games night, which is organized at the conference, which is kind of a fun networking event. And I spent the whole night playing Hanabi with him and his whole group that was there at the conference. Hanabi is this really great game. If you don't know it, I definitely suggest you do it. It's a collaborative game, very smart. You have to think, and then you can blame the others for making mistakes and so on, even though it sounds nice that it's collaborative, but it doesn't work like that. But after a night of playing this game with the group, like I got the offer to like join the team and get a postdoc there. I was like thinking about the other options as well. I approached like a couple of other people that I knew from the best papers, like these are the people I want to work with, but it didn't really work out with any of them. So eventually it was decided that I was going to the University of Alberta, and I found out that not only like Mark Langto wasn't there, but Mike Bowling was there, but Csaba Szepesvári, which was like the author on the Monte Carlo research paper, was also already working at the University of Alberta, and they had a very nice like AI reinforcement learning group going on with Rich Sutton, which you may know, and so on. So it was really a great place to go. Did I wanted to have some lessons learned here? Yep. So know the best in your field. It's not that hard. Really just notice who wrote all the papers that you are reading. And then it's maybe easier to start collaborating with the juniors. Like going directly after the professor is probably hard because they are super busy people. But if you take their students, their recent graduate that is doing postdoc somewhere or got a position somewhere, you start collaborating with them. They are very likely still very well connected, and they can give you reference. And reference is super important. Like when we are talking about networking, it's not only about who you know, but also who knows you and who can just vote for you that you are a normal person, right? It doesn't need to be that you are the smartest person ever who will do everything. But if somebody votes for you that you will probably deliver on whatever, you will show up to work every day, you will just keep working, it's already super important, and it gives a lot of comfort to whoever like might be considering hiring you. So really trying to start collaborations even with the kind of wider network of the person you are actually interested in working with is super important. Okay. So UFA, again, place with ambitions, poker group which was doing research in poker for 10 years, and it was the right time to have a great result. And we were not shy about that. We just decided that it's the time to beat the best professional people. And we were working for a year on just this single project. Like, okay, not just this single project. I had like 2 more papers from that time, but like 80% of time was spent only on this project, and it eventually worked out. And it was a team of 10 people working really for a year, mainly on this, and we got it into science, and it was again a huge door opener. Like once we got this result, it was huge media coverage, like an interesting place. We got actually offers from many places that we could like join, make a startup, that people were willing to fund us and so on. And eventually the group agreed with Google that they'll start a new DeepMind office in Edmonton. And like all the senior researchers got an offer to join it. again, for some personal reasons, I needed to get back to Europe, so I didn't take this offer. But still, like being part of all this helped me a lot when I came back, where again it was easy for me to write some proposals, get funding from the Neuro Foundation, from Gutcher. Like it was rather easy to then bootstrap my own group when I came back here. So that was the part of the story that I wanted to share, and now I just try to sum it up in a couple of points. So go abroad. Why? Because there is a lot of personal growth and fun in it. Like really, one of the reasons why I was doing PhD was actually to be able to travel and meet new people and understand new cultures. It's really important to build CV. Like it sounds very superficial, but if you are then thinking about joining places like DeepMind, like OpenAI, like these huge labs, which are getting like thousands and thousands of applications every week, if you don't have something in your CV that stands out, or even better, if you don't have like some kind of reference, somebody who is already working there, somebody you knew that can like recommend you, then it's very hard to get even in the interview, to get even the chance to show them that you are up to it, that you are really good. Don't be afraid of ambitious projects. Really, you are spending, or researchers are spending a huge amount of time on projects which maybe are not that important, just because they are afraid to go directly after the very hard thing, after the really, really big ambitious thing. Do it. And if you go abroad to the universities where this is normal, you will find people who will support you in this, because they will consider it normal that you just do the big thing. You will be able to get better collaborators and peers. Like on average, people at the good universities are actually really much better than the average person you can collaborate with here. You will get more citations, which is really the currency of research. That's like everything that matters, or not everything, but huge thing that matters in your research career. If you know people, they will cite you, and it's not some kind of fraud. It's really just how people work. Like they will just think of you more if they know you personally. Later in the career, you will need to write all sorts of funding proposals. And again, since the collaborative funding is somehow preferred very often, if you have friends around the world which you can like write these proposals with, it's again much easier for you to do this research. And then for student exchange as well, like getting somewhere through your advisor, or getting as later as an advisor, getting some smart students from abroad from your contacts is a super good reason to travel. So this is why I think you should do it. And then maybe just to keep in mind why the others are doing it. That is also not just like charity from their side. So companies generally accept like students for internships, or young researchers for internships, mainly because of hiring, right? Like they want to test you, they want to work with you for a couple of months and see whether you are good enough so that they would actually give you an offer. So that's why they have all these programs, that's why they are willing to accept you. You don't have to be like feeling like you are somehow like pushing yourself there. No, they want you, they want to try you, and you can have this opportunity. Then sometimes they use it to collaborate with academia, right? Like if, again, you have an advisor who has this relationship, but he doesn't want to spend all of his time at the company trying to understand their problems, they can just send their student there for some time to build this relationship. So it's actually beneficial for everyone if you think about it. Academic institutions as well are very happy to accept students because they are looking for these kind of smart students from maybe weaker universities that cannot give them their support. And it's very good for them because they can have them for a couple of months. If they are great, they will continue collaborating with them. If they are not great, they will be gone in a few weeks, few months, and it's fine. So really don't be afraid. There is something for them as well. So just try to use it. There are these collaborative projects that everybody is kind of pushed into, and it's a good way to go somewhere and meet somebody learning something new, and also the academic institutions, like often when you want to go for a postdoc or a PhD, having some visit before for a couple of weeks is a great way to do it. How? So these are just the basic options. Summer schools are good very early in the career. I wouldn't advise it after like 2 years of PhD. Then probably you should already go for proper conferences and get to the doctoral mentoring programs and all of the support networks at the conferences. Most conferences do have them, so try to look at them and use them, because they are very targeted on networking and on, like, getting you mentors from related fields, like helping you grow. Erasmus, again, most people here use it just for master's or bachelor's studies, but you can go for Erasmus also during your PhD. So try to find out more details. Try to go somewhere where somebody is doing something similar. Masters and PhDs. That's, I think, a very good way to go somewhere. Even for second masters, like people at the University of Alberta generally didn't want to take PhD students because it was too big of a commitment for them to like get somebody they don't really know for 5 years. They didn't want that. So even if somebody had masters before, they would go there, take another master in a year, give this kind of trial period, which can gracefully end with just getting the master and going on and it's kind of fine for everyone. But if they click, if the person works well, then they can continue and do PhD with these great people at a great place. So consider even this. Don't be afraid, really apply. That's cheap. Like, you will get rejected, you will get used to it. It's part of life. But if you don't try, then you have no chance to succeed. And another thing which I cannot stress enough are cold emails. They just work in science. Like in sales, they don't work probably that much, but if you see a paper that you like, that you are interested in, if you reach out to the authors, they will very likely, at least for the first email, be careful about how you phrase that one, they will respond rather quickly, and they will be interested in talking and collaborating and so on. They can get bored very quickly, so really try to be efficient, but don't be afraid to approach anyone and start collaborating. Like, offer them that you will like figure out some problems for them as part of your studies, as part of your research, whatever, and they are very likely willing to do it. So build relationships with people. That's the first thing. Like, wherever you are, at conferences, at research visits, at summer schools, wherever, ask questions when you are at the conferences. Like, be seen. Like, there are hundreds of people. If you are the one who stands up, says something, then you will be remembered for the next few days. If you then reinforce it by going to talk to the person at a poster or something, they will remember you for the next year. And that's like very important step to have open like door for some collaboration, possibly later some internships and similar things. Publish and promote your work. Like, there was the whole talk about it right before. Again, there is just so much noise that being just a little above the noise is great. Aim high initially. Like, you will not give too much for the rejection. If you are rejected 20 times, then maybe start aiming lower. But try to go as high as like you can. Sky is the limit. And when you do something, like when you go somewhere, try to wrap it up with a public result, like at least a GitHub repository or archive tech report, like something that you can point like, yeah, I did this when I was there. Because then if you have like 4 internships and there is nothing you can point at, like this is what I did, then it's also not great. Okay, so that's pretty much all I wanted to say. I think Lenka wants to shut me down anyway. Networking is super important in science for getting the opportunities, for getting the students later, for getting grants, for getting citations, for like networking is really way more important than I would like. I understand like smart genius in their room who is doing their great results, but then if nobody reads it, nobody cites it, nobody knows about it, then it's kind of useless. There is a lot of luck involved, like definitely, but you have to be open to get lucky. You really have to get exposed to the opportunities in which you can eventually be lucky. And when you look only at the successes, it looks like somebody just got it all, but you don't see all the failures in between, which need to be there. And just by rolling the dice many times, you will eventually get lucky. And then there is this domino effect. Like once it starts rolling, it's easier and it's easier. Like the first couple of successes, it's hard, but then people will start notice, you will get the network, and that will help you succeed further. So thank you very much, and we will have some discussion tables where I'll be happy to discuss any details of this even more.